Let us begin the next session. This presentation will explore the possibilities of automatic extracting example sentences from corpora and mapping them to the appropriate sense of the word. Now, I'm sure many of us are interested to learn whether that is possible. It is joint work by Alexander Geyken from the Berlin-Brandenburgische Akademie der Wissenschaften and Christian Pölitz, Thomas Bartz from Dortmund, please.
Thank you for the introduction. So just to be sure, and I hope you won't run away if I say we haven't solved the problem, but we have overcome, let's say we have met some steps, done some steps beyond the first difficulties, perhaps. So Christian Pölitz, to be precise, he is part of the machine learning group at the Technical University in Dortmund. Thomas Bartz is a lexicographer there. So especially for the technical points, Christian would be responsible, but I think the principal questions are raised in the topics I will explain. So the motivation behind this is it is true for every large documentary, monolingual or bilingual dictionary where you have a lot of entries and you have to maintain examples in that dictionary, because quickly, if you don't go through them from time to time, they will get outdated. You might also want to add more examples or more genres, and in all these cases it might be very helpful to get semi-automatically assisted by methods extract the appropriate information from corpora. So almost everybody here will be familiar with the Godex paradigm that dealt with extracting automatically good examples from corpora. I think everybody who has worked with corpora has seen there are many bad examples if you go through concordances. So this task solves the problem we tackle here mainly for monosemous words. For polysemous words, the problem, or I would say what one would like to have is to link it to the appropriate dictionary sense to make it less hard for the lexicographer to handle these cases afterwards. So this task is embedded in a project where I come from. This is called DWS, Digitales Wörterbuch der deutschen Sprache, Digital Dictionary of the German Language. It's run at the Berlin Academy of Sciences and Humanities. The poor humanities are a symbol here because they otherwise, if I write it in complete words, would have taken one line, and given the poor funding in Germany, it's about the proportion. So we compile, the goal is to compile a large corpus-based synchronic dictionary based on basically two dictionaries. One is from East Germany, compiled between 1961 and 1977, the Wörterbuch der deutschen Gegenwartssprache of contemporary German. And the other one is the Duden, I think from the color, and might imagine which one comes from which part of the German side, even though. So what we have to do is we have to administrate almost 500,000 dictionary entries. More than half of them come from the historical dictionaries, the Grimmsches Wörterbuch, and the other one, almost 200,000 entries, are from the synchronic. We have a large corpus-based 5 billion tokens, which gives us a lot of choice to extract corpus examples. So from reference corpora, from national newspapers, and from mediated communications or internet corpora. We have also word statistics, timelines, and word sketches. And so what the ultimate goal is to have an aggregated form of presenting the entries. Here, an example, the word lighter, which is highly polysemous, which will be the example for the rest of the talk. Lighter can mean on the one time the ladder that you climb on the other hand, could mean the head or the conductor in the sense of semiconductor. So in the, what I will present now is the resources first, then the research question is embedded in the word sense disambiguation paradigm. Then I will say a few words about the method. We have done a first experiment, and then perhaps the interesting part will be about the results and the insights for further work, which is definitely necessary, that I will the conclusion. So the resources are legacy dictionary. What you need, then you need some knowledge in order to improve the results. The knowledge we had at our disposal is a database, a large database of collocations. And of course, since we want to map corpus examples on dictionary senses, we need a corpus of example sentences. So as I said before, the legacy dictionary, I take here one of the two, the one from where we are the full copyright holder, consists of 90,000 full entries and a bit more than 200,000 usage examples of patterns. The collocation database is, contains 12 million collocations, and it is done in the same way than word sketches. That is a statistical measure, and we have syntactic relations. And in order to extract the corpus sentences, we make the first filter with a Godex algorithm we have implemented in Berlin. So in order to remember some of the features of the word sketch engine or of our equivalent for German, so what you extract is syntactic relations of two words, three words, and then to collect them, and this will form your database, your successful, there are collocations, if not there are co-occurrences, but in any way there are valuable knowledge that any system, any machine learning system can work with. So in order to show you what the problem is, here's one example again for ladder. So the first sense is the ladder. The sense number two is director or the head of something. And here this sense is expanded sense number two. Here we have made up examples and constructions with, and the second part are the corpus examples. So a sense for us is not only the definition, but the definition plus made up examples plus corpus examples. So that gets you a richer possibility to learn something. And I've only expanded for reasons of space here the sense number two, but of course the other senses also have the corpus examples and made up examples. What you can already see is the example is from 1960, and of course, what one would like is to update this appropriate example, appropriate sense that is slightly newer. Those who are familiar with machine learning, and even those who are very far away from this topic, know that there is a famous research field, word sense disambiguation, that looks very much like the problem we have at hand. I would say the different domain is here that we don't compare a sentence to definition, but that we compare a sentence to a definition plus additional examples given by the lexicographer. So we have normally more to learn from dictionary sense than from definition. So in the history of word sense disambiguation, the most simple way was to take the overlap of words in the text with words in the definition or words in the synset. Then other things were used, like additional knowledge about paradigmatic information such as hyponyms, and syntagmatic information such such as collocation databases. And more recently, supervised machine learning techniques were employed, such as, and there are a number of them that are enumerated here. The one we use is the last one in the row, the maximum entropy classification. But of course, it would be interesting to do the same experiments with other learning methods. The method, I have to be quite brief here, but the main idea is to pass the idea. The step one is to select the keywords in the dictionary. So we took keywords that were polysemous in order to have, well, realistic keywords. Then we compute the good example sentences for each keyword. We initialize the knowledge base, that is, we extract and lemmatized all open word classes, that is, adjectives, adverbs, nouns, and verbs for each sense of each keyword. And then we enrich the knowledge base by computing the set of all collocations for these content words. And if we manage to have GermanNet as well for our experiments, we could do the same thing for the paradigmatic knowledge. Step number 5 is to annotate by hand the senses for each of the extracted examples. And step number 6 is determine the best sense with 2 algorithms. One is called the LESC algorithms, which works more or less by intersections of words. And the other one is the optimized machine learning. So in order to give you a better impression, I have an example. So LESC, initially developed in 1986, proposes to choose the sense that has the maximum number of intersecting words, which is quite intuitive. And we have a second implementation of LESC that takes the maximum of the sum of the log dices, so just weighted by the collocation strength. So what happens here is we have, on the middle, we have the dictionary definition. Leiter, sense 2 is something directs something, with a proposition of something. And here we have extracted the content word Spitze. And in the corpus example, we have extracted another word, a content word, Verantwortung, responsibility. And then what we do is we build the intersection between Spitze and Verantwortung. We draw the sum of all the first we extract all the collocations. Then we build the sum of all the collocations that are in the intersection. And we do this for all words. Of course, this is a task very well suited for machines, not so well for us, but the machine can do this very quickly. So we go all over collocations, and the sum at the end, what I will show you here, is that we find 86 collocations that are in common between Spitze and Verantwortung, and a log dice sum of almost 800 for sense number 2, and a log dice number of 62.95 for sense number 1. So the result is the system in this case will find sense number 2 as the appropriate sense for the corpus sentence, which is in fact the truth. I won't go back. Trust me here. But this case is not very difficult for the system. It's not a case where the machine learning approach has any advantages, but I will show you one example afterwards. Matters. So what we have confused now, or what we have uniform way, we have for each relation, syntactic relation of the collocation, give weight. That is, adjective noun has the same weight like coordination or like adverb verb. Of course, one might think that giving different weights to these syntactic relations might improve the results. And that is what we effectively do when we consider that the relations as a vector, and we draw the sum of the aggregated log dices for each relation. And then we assign the best weight to each syntactic relation. To do this, we use this maximum entropy classifier. And this models the probability distribution of a given context and a given definition from the senses. So what our second method does is that we learn the correct mapping between example sentences to its sense number based on, that's why it is called supervised and hand-labeled sense annotations. The implementation was inside the RapidMiner platform that is, has been developed at Dortmund. Now it is a mid-sized company who develops learning algorithm platforms. So in an experiment, we have reproduced these steps with 100 polysemous words from our dictionary, 75 nouns, 25 verbs, that had a total of 857 senses, 314 main senses. So here are some examples, and in parentheses we have the number of ambiguities. So axis has, for example, 3 senses, lighter has 3 senses, and so on. Step 2 is to select corpus examples with the Codex algorithm. We extracted the content words and lemmatized them. Then we hand-labeled them with the senses, that is to each corpus sentence, we associated by hand the correct sense. We had 2 annotators. The agreement was by 78%. So you have to keep in mind that 100% is not possible if one tends to think so. The step 3 is we have computed the collocation database, and the step 4 is to compute the LESC and the ML method. I have to go quick here because I have 4 minutes left. The training set was on 50 keywords or 1,000 examples, and the evaluation on the remaining 50 keywords. So the baseline would be, supposing a little bit more than 8 senses, baseline would be, pure chance would be 11%. The LESC algorithm would provide 31%, and the machine learning approach 9%, with a difference between nouns that work better than verbs. So one example where the machine learning approach works better than LESC is the following one. The English sentence, the central sentence, then the couple is accompanied by the sounds of a Te Deum, orchestra or church. In German, this would be ambiguous. LESC says here, well, this is the orchestra, which is quite strange. In this context, it is clearly the church. And the MEC would link this correctly. Just one example from the corpus. Another question one could raise is, if you don't take the fine-graded senses but the coarse-grained senses, does the result, how does the result vary? It does, in fact. The baseline would be 31%. MEC would give us 55% in this case. The nouns work even better, whereas the verbs don't work as well. Also, the inter-annotator agreement is better for coarse-grained senses. Possible reason for this that Codex gives higher priority to regular examples. This does not achieve, yes, I quote from Cook and Rundle and other persons, the contextual diversity that characterize example sets selected by skilled lexicographers. So one has to work also on the variety of expected example sentences. And another finding is that Codex selects the first sense as a baseline in 55% of all the cases. Also not optimal. Conclusion, this is my last slide. Fine-grained machine learning approach works better than the older LESC approach, so it's apparently worth trying machine learning methods. The coarse-grained is just as good as the first sense baseline, which is kind of a deception, but one might suspect that the skewed Codex input is to somewhat responsible for this not so positive result. But there is hope. MEC or other machine learning techniques might improve if you add more knowledge, such as synsets, synonyms, hyponyms, and so on from other knowledge bases. You could also experiment with different feature selections, Here we have just done with a standard way with collocations, but could also vary here something. And another point is that the dictionary at hand has also its own characteristics. So it might be if you have a newer dictionary with more examples, then you augment the knowledge base. It also might help you with a richer sense description. And this also would give us some hope that this might perform better if the dictionary increases its senses. So I will end here, and I'm happy to answer.
Yes, let's get on with it. Questions here?
Since you're dealing with a legacy dictionary, there are bound to be some senses missing. Is there some kind of control on that? Is there, what if an example belongs to a sense that's actually not in the dictionary? Is there some minimal threshold for the log dice value to say, well, apparently it's not similar to any of the senses we have in our dictionary. This must be a new sense, something like that?
Well, thank you for that question. First of all, the collocations are blind with regard to the senses, because they're simply co-occurrences computed statistically from large corpus. Right, but I suspect, even though I haven't checked the database for it, that the log dice value doesn't predict very well if this is a new sense not contained in the dictionary.
I had one question for the task, which was to find example sentences for dictionary entries. It would seem to me that what you need to do is find sentences that contain the word in a specific sense. Right. Then it seemed with the example of Capella that you're trying to do the opposite, which is to recognize what sense a word is in an example sentence. And I wanted to understand which approach you took and which approach the statistics, the 55% and so on. Which approach does it relate to?
You repeat the first way. The second way is what we were doing, but the first way is in what sense?
The first way is to find example sentences in which you know or in which the algorithm thinks that the word is in a specific sense, which is a much easier task than to recognize the sense of a word in any given sentence.
I'm not sure that I've well understood your question, but how can we know, even say that this is a task, it's interesting too, but how do you know that the sense in this sense of a word in this specific sentence is number 2 or number 3?
Well, we in my company we call this active and passive word sense disambiguation, and the active one is when you go and search for sentences that match the criteria which you know identifies a sense reliably, whereas the passive one is given any random text, try to recognize the sense. And the first one you achieve much higher accuracy rates, and that would seem to me the appropriate one for this task, which is find example sentences for a sense. And so I was surprised about the low accuracy numbers.
Thank you very much for this hint, and
maybe it's it's a hint.
Good for this, and perhaps for other persons that might be.
So you were doing the second approach, right? Trying to identify this. Okay, just one.
Yeah, one last question.
So I wasn't quite clear what the feature set that you used for the maximum entropy classifier was. Is it just grammatical relation types, or are you weighting more features of the context and so on?
Well, right now this is the first experiment we have conducted. We just took the relations. That means 12 relations. We have 12 syntactic relations, and this gives us a feature of length 12. And what we do there, we collect all the co-occurrences in our database, and we draw the sum of it. So that's all. Just 12 or 13 features.
So the type, there are 12 types, but instances are collocations within each type.
So many more. So if you call this, I would call one feature adjective noun, and inside adjective noun we have for a given word all the collocations that correspond to this given word.
Yeah, I guess
gives
what
us
I'm
a
trying to
con-
ask is, are the feature instances actually the lexically specific instantiations of the adjective-noun link, or is adjective noun the feature?
No, the latter for the moment.
So that it's the lexically specific version.
Yep.
Okay. You thought about trying to use some kind of notion of lexical similarity there, because that's going to be very sparse, right? You know, most vectors are going to be 0 in the
Right.
machine
There's-
learning algorithm.
Definitely there's room for improvement. I only stick to the first part of my claim, that is a practically relevant problem. And I'm also presenting here in order to learn about different approaches. And this might also be some way.
Okay, and
Okay.
that ends this presentation. Thank you very much once again.